All right, hello everybody. We're back with another question, and this is a paper 2 question from the SL paper from the November 2019 batch. So one of my followers on my social media page had requested me to do this, and so here I am. I oblige and I'm doing this. And just like that, if the rest of you or anyone else watching has any questions, please feel free to send it my way on my social media or email it to me or just drop down a comment below, and I'll get back to you as soon as possible. All right, so this is question number 3. Let's see the question. The following shows some compounds which can be made from ethene, which is C2H4. And they've given us the reaction, a series of reactions actually, where ethene is being converted into first a halogenoalkane, and then it's being oxidized, I believe. And after that, it is undergoing further oxidation. All right. So first, state the type of reaction which converts ethene into the halogenoalkane C2H5Cl. Now, as you can see, ethene is an alkene, meaning there is a double bond between the carbon. Now, in order for it to be converted into this molecule, which is C2H5Cl, you can see that the double bond is being broken and you are adding a hydrogen and a chlorine. Therefore, this type of reaction is called an electrophilic addition reaction. So I'm just going to type it out because my handwriting is absolutely terrible. So it's called an electrophilic addition reaction. Now, what is an electrophilic addition reaction? But to understand what that is, first let's understand what an electrophile is. So an electrophile is basically any chemical or any substance which is attracted to electrons. That's why it says electrophile. So you can kind of imagine that it loves electrons. So you know that electrons have a negative charge. Now, what is attracted to a negative charge? A positive charge. Anything with a positive charge is attracted to electrons with a negative charge. So the reagent, which is the electrophile, has to have either a positive charge on it or it should be deficient in electrons in some way or the other. So it should be able, the electrophile should be able to accept a pair of electrons. Now, this electrophile can be just about anything which can act as a Lewis acid or which can accept a pair of electrons, right? It can be an individual compound, so it can be something, it could be like an hydrogen, it could be an H plus, just an individual H plus, or it could be a compound which is very polar. So you could have a compound like HCl. I'm just going to erase this over here so that we have some more space to work this out. So you could have, yeah, like I was saying before, you could have an compound which is extremely polar. So you could have something like HCl. And you know, or based on previous knowledge, or even you could even look at this in your data booklet, that chlorine is highly electronegative. So it has a tendency to attract electrons towards itself. You could think of it as a magnet for electrons. So that's why in this whole compound, the chlorine kind of is the dominant one. It is going to pull these electrons from the bond towards itself, and this will give the chlorine a slight negative charge. Whereas the hydrogen, which is not as electronegative, will now get a slight positive charge because chlorine is pulling everything towards itself. Now, in this reaction, the electrophile is actually the hydrogen because it is being given a slight positive charge and it can accept a pair of electrons, but not in this state. Hydrogen will actually have to break away from the chlorine and then go and attach to ethene. And when it attaches to ethene, it will actually break the double bond between the carbon. And then the carbon which has been left. So for instance, if this is what happens, so now this hydrogen has come and it has attached itself to carbon. And now carbon has broken the double bond over here. This bond has been broken so that it can attach the hydrogen. And now this carbon is deficient. It needs something else. It has a slight positive charge because the electrons from the bond which were being shared are now being used to keep this hydrogen over here. So when there's a slight positive charge over here, this is called a carbocation. You don't need to know this. I'm explaining this just so that you can understand. This is actually an HL concept, but so you understand what I'm talking about, I will be explaining it. So now since this hydrogen is gone and it has attached itself over here, I'm just going to erase this. You have a chlorine left with a negative charge. And this chlorine, which has a negative charge, will be attracted to the carbocation over here, which has a positive charge. So it'll take itself and it'll attach itself to this carbon. And that's how you get your halogenoalkane. So this is our final product. So that's why it's called an electrophilic addition. You have an electrophile and you're adding something to the compound. Now, let's take a look at the next reaction. I hope that all made sense. Now, remember, you don't have to know any of this. You just need to know the type of reaction. You need to know what an electrophile is. You need to know what an electrophilic addition reaction is, but you don't need to know the process. You don't need to know how it attaches, or you don't need to know about the breaking of the double bond. You don't need to know any of that. That's not in the SL syllabus. So let's look at the next question. It says, write an equation for the reaction of C2H5Cl, which is the halogenoalkane, with aqueous sodium hydroxide to produce a C2H6O compound, showing the structural formulas. So now it has said that the structural formulas, that means it's just going to be a word equation. Now, we know that you have the halogenoalkane, which is C2H5Cl plus NaOH. This is going to actually give us but before I tell you what the result is, you should know that this NaOH over here, it is a base. You know that it is a base, and it is going to produce a nucleophile, which is OH minus. Now, what is a nucleophile? A nucleophile is any substance which has either a lone pair of electrons or a negative charge on it, and it is attracted to a positive charged region in a molecule. That is what a nucleophile is. And in this case, your OH minus acts as a nucleophile. Why? Well, because it has a negative charge and it also has a lone pair of electrons. And if I draw it out, if I draw the Lewis structure of OH minus, you'll see what I'm talking about. You have O, you have it bonded to an H, and you know that O has 6 electrons. But since there's a minus sign over here, we add an extra electron to oxygen. And the hydrogen, which only has 1 electron, is going to bond to the oxygen. And that way you have a full octet for hydrogen and you have a full octet for oxygen. So that's how you draw the structure. Now you can see that it has 1, 2, 3 pairs of 3 lone pairs of electrons. So this OH is actually very, very high in electrons, and it can donate these to form a bond. So this OH minus there is a nucleophile. It is attracted to a region of positive, to a positive region. So when this OH minus is added to the halogenoalkane, so when this OH minus is added to an halogenoalkane, it causes this chlorine over here. This chlorine gets scared and it leaves. So this chlorine will break away from the carbon. And when it breaks away from the carbon, it actually takes both of the electrons in this bond. So you can think of it like a thief. It takes the electron that it contributed to the bond, and it also takes carbon's electron. So it'll take these electrons and it'll leave. So it'll form Cl minus. So it'll just come and sit over here and it'll form Cl minus. Now this OH minus, which it's scared of the chlorine, will go and it'll attach to the carbon atom, which now has a slight positive charge. It's called a carbocation because the chlorine has took away its electron, and it's took away the electron it contributed to the bond. So that's why it's left kind of with a slight positive charge. So this OH will go and bond to the chlorine. So now you end up with something looking like this. You end up with this. to an OH. And then this Cl minus over here will go and combine with the Na plus from the NaOH to form NaCl. So this is essentially something which is called nucleophilic substitution. Well, because the nucleophile, which is OH, is going and substituting itself in the place of Cl minus. So it chases away Cl minus, it kicks it out quite literally, and it will take its place. So that's why it's called nucleophilic substitution, because OH is a nucleophile. It is attracted to regions of positive charges. Now, remember, once again, you don't need to know this process. You don't need to know about that. You just need to know the reaction or what happens in nucleophilic substitution. And the only reason I've told you about this process and what happens is so that you have a better understanding of what's happening. This is actually only required for HL students. And if you're an SL student, you don't need to know about this. So what SL students should know is about nucleophilic substitution reactions, what type they are, and the very basics of how they occur. You don't need to know the process in detail or anything for that matter. So the products of this is C2H5OH plus NaCl, because as I showed you earlier, we form salt because the chlorine, which is being chased away from the carbon atom, goes and combines with the Na plus. Sorry, that looks like an S. This is actually a 5. So C2H5OH plus NaCl. So this is your equation. Now let's look at the next question. So C1. Write an equation for the complete combustion of organic product in B. So in this case, they're talking about the combustion of C2H5OH. And the name for this is actually ethanol. So the combustion of anything for that matter, is when you combine it with oxygen and you produce CO2 plus H2O. Now they have mentioned complete combustion. So that means that the reaction goes to completion, meaning all of the C2H5 is being used up or being burnt up in excess oxygen. So that's why it produces carbon dioxide and H2O. Now this equation is not balanced, so I'm going to balance it out. I've already done it, so I'm just going to put the numbers and the coefficients, and we can check after that if my balancing is correct. So it's 302. So I'm just going to draw this out on the side to make some more space. So C2H5OH plus 3O2 gives us 2CO2 plus 3H2O. Now let's check if it's balanced. So on the reactant side, we have 2 carbons, we have six hydrogens, and we have 7 oxygens. And on the product side, we have 2 carbons, we have 6 hydrogens, and we have 7 oxygens. So yep, this is balanced. So this is the answer for C1. I'm just going to draw this up here. I hope that you've understood what I have done so far. If you do not understand what I did above regarding the electrophilic addition or the nucleophilic addition, I would highly recommend you to go and read that in your textbook or the notes that you have made. Because these are, even though you don't have to know them in great detail, you still need to know what they are and the basics of what an electrophile is and other things that I mentioned before. Now, let's look at the next question. Determine the enthalpy of combustion of the organic product in B. So in B, we made the organic product, which is C2H5OH, which is ethanol. Now, they're asking us to determine the enthalpy of combustion, using the data from section 11 of the data booklet. Now, just a quick exam tip, be very, very careful which section you use. If they have said to use section 11, only use section 11. And if you flip to section 11 of your data booklet, you'll see that section 11 mentions the the different bond enthalpies between different elements. And that is what you have to use in order to calculate the enthalpy of combustion. So we know what the formula of enthalpy of how to calculate enthalpies using the bond enthalpies, or the enthalpy of combustion using bond enthalpies. It is the bonds broken minus the bonds formed. So this is the equation for calculating the enthalpy of combustion using bond enthalpies. So essentially what this means is that we have to calculate the bonds broken on the reactant side, which is with the ethanol, and we have to calculate the bonds formed on the product side, which is carbon dioxide and water. Now, the best way to approach this question is to first expand the formula and to draw them out in their in their structure, in the structural form. So what I mean by that is you draw it like you would draw a Lewis structure, for example. And now then you start to count the bonds. So you can see that you have 1, 2, 3, 4, 5 C to H bonds. You have 5 of them. And if you look at your data booklet, the bond enthalpy for a carbon to hydrogen bond is 414 kilojoules per mole. And since you have 5 of them, you multiply this by 5. And this gives you a total bond enthalpy of 2070. Then you look at the other bonds. You have one carbon to carbon bond. So this one carbon to carbon bond has an enthalpy of 346, and you only have one, so you leave it like that. And then you have one carbon to oxygen bond. And this has a bond enthalpy of 358. And then you have one oxygen to hydrogen bond, which has an enthalpy of 463. Now you add all of this up, you add all these numbers up, 2070 plus 346 plus 358 plus 463. And this gives you a total enthalpy value of 3,237 kilojoules per mole for the ethanol molecule. But our step isn't over here. Remember, we are also breaking the bonds between the oxygens over here. So we have to also include that in the bonds broken section. Now, you know that O2 has an oxygen which is double bonded to another oxygen. And the bond enthalpy for this is significantly higher than one for a single bond, because double bonds tend to be stronger than a single bond. So the bond enthalpy value for an O or oxygen molecule is 498. And since we have 3 moles of that, we multiply this by 3, because you look at the coefficient there, 3. And the answer for this is, I have to put that into my calculator, it is 1,494 kilojoules per mole. Now we add this value with this value, and we get a total enthalpy of the bonds broken. So these are the bonds that are being broken. So the total enthalpy is 4,731. So the total enthalpy is equal to 4,731 if you add both of them together. So the bonds broke. I'm just going to erase all of this. So the total enthalpy for breaking the bonds, the total enthalpy that you require for breaking the bonds is 4,731 kilojoules per mole. So I'm just going to keep the equation here, bonds broken minus bonds formed. So this is 4,731 minus, now I've already calculated the enthalpy of the bonds formed. Now I'm not going to show that how to do that again because I've showed it to you while calculating the bonds broken, how I did it while calculating the enthalpy for the broken bonds. So you can do that also. It's the exact same process for the bonds for calculating the enthalpy for the bonds formed. So I'm just going to save some time and I'm going to quickly show you what the answer is. So that is the enthalpy for the bonds formed. Now we subtract these and you get an answer of negative 1,263 kilojoules per mole. So that is your final answer. So that's your final answer. And just a quick reminder before you go into your exam, be very, very careful when you're calculating the bonds, when you're counting the number of bonds and be very mindful of the number of moles of the substance that are there. If there are 3, then you multiply the total bond enthalpy for one molecule of H2O by 3 because there are 3 molecules, and so on and so forth. Just like I did for oxygen, you should do the same for CO2 as well. So the next question. State the reagents and conditions for the conversion of the compound C2H6 ethanol produced in B into C2H4. Now, C2H4 looks like this, right? And if you can tell, this is an aldehyde because this is the aldehyde functional group over here. And you know that the alcohol that we produced in part B can be oxidized into the aldehyde over here. Now, in order for you to oxidize the ethanol, we need a few reagents and conditions, and that is what they are asking us to state over here. So now this is something that you just need to know and kind of actually remember, because this is something that you are expected to know actually. And if you do not know what I'm talking about, I would highly recommend you to go and look at the conversion conditions needed to convert or to oxidize a primary alcohol like ethanol into an aldehyde. So the conditions are actually, you need first a reducing agent, because if you want to oxidize alcohol or sorry, ethanol, you need a reducing agent. In this case, the reducing agent is Cr2O7 minus. So this is called potassium dichromate. The name of this molecule is potassium dichromate, and it's a strong oxidizing agent. The next, we need a, we also need something called H2SO4. And now if you know what this is, H2SO4 is essentially sulfuric acid. And this acid provides us with H plus. And this H plus is necessary in the reduction of potassium dichromate. And the last condition that you need is you need to be able to distill. So this reaction basically takes place in a flask, and you heat the flask with the alcohol the reducing agent and the sulfuric acid all mixed, you heat it, and as you continue to heat it, you'll slowly start to form the aldehyde which you require. But if you continue to heat it and you don't distill the aldehyde away, this aldehyde will be further oxidized into a carboxylic acid. Now, this will only happen, the further reduction can only happen in a primary alcohol. You cannot do this in a secondary alcohol. In the secondary alcohol, you can only distill it, or you can only oxidize it to a ketone. You can't oxidize it beyond that. So in a primary alcohol, if you want the aldehyde, you need to distill. So that is the last. This is a D. Distill. Now, the third question, second part of the third question. Explain why the compound C2H6 produced in B has a higher boiling point than compound C2H4O produced in DI. Now, why the compound C2H6, which is an ethanol, has a higher boiling point is because of the intermolecular forces between the alcohol, or the ethanol molecules. Now, the intermolecular forces between the ethanol molecules is hydrogen bonding, meaning ethanol can actually participate in hydrogen bonding, because if you look at the structure of ethanol, it has a hydrogen which is attached. This hydrogen over here is attached to a highly electronegative atom. So this has a slight negative charge and this has a slight positive charge. And this hydrogen with a slight positive charge can actually this hydrogen with a slight positive charge can actually form attractions with an oxygen on another ethanol with a slight negative charge. This is how hydrogen bonding takes place. This is essentially the hydrogen bonding, and it is one of the strongest intermolecular forces. That's why ethanol has a higher boiling point than C2H4O, which is the aldehyde, because the aldehyde cannot participate in hydrogen bonding. The only intermolecular forces that the aldehyde will have is dipole-dipole interactions, because the hydrogen is not attached directly, not attached to any highly electronegative atom like oxygen. So that's why there is no hydrogen bonding in the aldehyde, and that's why the boiling point for this substance will be lower than that for the ethanol. So I'm not going to write out the explanation, but I've given you a gist of why the boiling point of ethanol is higher than that of the aldehyde. Now the last question. Ethene is often polymerized. Draw a section of the resulting polymer showing two repeating units. Now, these questions are actually one of the easiest to solve, and you can score marks very easily on this section because of how simple the concept is. Now, you know that ethene is an alkene. The structure is like this. Now, polymerization is when this ethene, you break this double bond over here and you sort of just move these hydrogens up so that it's easier to show you what I mean. So you break that double bond between the two carbons, and on both sides you attach another one of the same unit. You attach another alkene which also has a broken double bond. So you can see that this is one unit. This is ethene with a broken double bond. This is also ethene with a broken double bond. This is also ethene with a broken double bond. And how they are stable is that they have attached to each other. They've kind of grouped up together and they form long chains. So this is just a very short chain. These chains, they run in millions and millions of units. So you have millions of units of ethene. And obviously I can't draw that over here, and they're not asking you to draw that either. They've just asked you to draw two repeating units. So this much should actually be enough. You have two repeating units. So this, and now to signify that the chain, this polyethene repeating unit chain runs on in both directions, you can signify it like this, with these squiggly lines, which tells the examiner that um, that these chains run on, and you know what polymerization is. And if you want, you can also put these square brackets around them, and you can put a little n over here. This n signifies that the number of units. So it's just n number of units. It could be an infinite number of units. It could just keep going on and on and on forever. So this is how you polymerize ethene. It's very simple. Just break the double bond, just remove the double bond, and attach this ethene to another ethene with also a broken double bond. Easy. So now that is it for this video. I hope that I've helped you understand the concept, and I hope that I've cleared any doubts that you may have had. If you have any further questions, please message me on my social media or send me an email or put it down in the comments below, and I will be more than happy to help you with whatever doubts you may have. That's it for today's video. Thank you so much for watching. I will see you in the next video with another question.